Let's do this thing. Okay. It's been a whole week. Feels like just yesterday, though. Or maybe not. We finished chapter 3. You can sort of say goodbye to probability for a little bit. We'll still be finding probabilities, but not in the same way that we were in chapter 3. Okay? And I hope you checked out, I posted that bonus assignment on random variables. It's a bonus assignment because we didn't talk about it in class, but I wanted you to be able to do it because you can still read the section and complete the assignment if you want to, and it'll just replace your lowest assignment grade. But if you decide not to do that one, that'll be your lowest assignment grade, so it'll get bumped. So no harm, no foul. But I encourage you to try it. Check it out. It will not be tested, of course, so don't worry about that. It's anything that's labeled bonus will not be tested. Today, we get into sort of getting close to my favorite part of the course, which is chapter 5 and onwards. But 4.1 builds the foundation for everything that we need for the rest of the course, okay? And so there are other sections in chapter 4 where we talk about distributions of random variables, okay? But of all those different distributions, the normal distribution is going to be the most important one, okay? What do we know about the normal distribution already? Well, we know that it's a shape. And that shape looks like this. And we know that it has some mean, which we can denote by a mu, right, for the population mean. And it has some standard deviation sigma. Okay? And what we'll find today is that, and we've seen it just briefly, we've seen it before, that we can fit roughly 3 standard deviations before we run out a curve. Now, here's the crazy part. This, see how I left a gap here? That doesn't close ever. It keeps going. So it's open all the way out to infinity. And so this curve never closes on the x-axis in either direction. So here, it keeps going, and there's a gap between them, very, very small. Now here's where it gets extra mind-boggling. The total area under the curve is 1. It is exactly the same as the probability of the sample space is 1, right? If I consider all my possible options, right? All my possible options from negative infinity to positive infinity, right? Of course, now we're dealing with a numerical variable, right? So it's on a number scale. And so if I consider all my measurements from negative infinity to positive infinity, it makes sense that that is my sample space, right? And so now my total probability, I gave it away. That was an accident. I slipped up. Forget I said it. No. Let it sink in. The total probability is 1. Okay? But I will call it this instead. The total area under the curve is 1. Okay? But the area under the curve is a probability. Oh, that's annoying. Let's do this again. Should be better. So the area under the curve is a probability. Now, if you've done calculus, right? Then, you can integrate between 2 points. This is Calc 2. And so then you can integrate and you can find the area under the curve. We don't want to do that though. No, no, no. So hence the table that you got today. And this is just someone sat down and did a bunch of calculus for us, wrote it down in a table. And this is very ancient stuff. We don't really use tables, but for tests, it's kind of the easiest way to give you these probabilities, right? These areas under the curve. Now we're going to parking lot that table just for a little bit. It's called the Z table. And so we'll introduce it later today, but we need to learn more about the normal distribution before we can do that. So, a couple of facts, right? The total area under the curve is 1, which means that if you know, for example, that the area to one side maybe is 0.6, then what must the area to the other side be? Must be 1 minus 0.6, which is 0.4. Now, because the areas are probabilities, we still only work with decimals, right? And so here, areas under the curve, curve, are probabilities. What do we know about probabilities? It's kind of what we're taking out of chapter 3 into chapter 4. The probability, any probability of A has to be between 0 and 1. Right? That's still a fact for all probabilities, right? And so the probability, any probability has to be between 0 and 1. Okay, let me go close this. I always teach in this room every single term. So I'm kind of bored of the room. I don't know, you kind of entertain yourself by the room. But it is nice because I can close that door and I know that there's a secret kind of in and out for you guys still. So that's a nice thing about the room. Okay, 2 nice things about the room. We have the periodic table of elements. Oh, that seems temporary, but hopefully, but that's really cute for today. So ladybug, 2 doors, that's pretty good. Anyways, probabilities have to be between 0 and 1. Okay? And so what we're going to do is we're going to use the table to find areas under the curve, which are probabilities. Okay, let's see here. I think that's good for, I'm trying to not do every slide on the first slide because I normally do that. Like, here's another thing you need to know. So the normal distribution, as we know, is unimodal, it's symmetric, and it has this bell-shaped curve. Now, what's neat is there are so many things that follow a normal distribution. And so a lot of things just naturally follow a normal distribution. None of them are exactly normal, but a lot of them can be approximated by a normal distribution. And even things that you wouldn't think follow a normal distribution can follow a normal distribution. In terms of notation, you'll see this notation quite a bit. Okay? And so let's talk about how we read this. So this capital N is the normal distribution, right? And so it follows, something follows a normal distribution, that's the shape, right? And then in brackets with a center at mu, right? So that's the center, comma, sigma, which is the spread, right? And so here, this is really just a shorthand of shape, center, spread, like we talked about in, I don't remember when, weeks ago at this point. And so here, right, this is the shape, center, and spread. So for example, if we are told that something follows a normal distribution, 30 and 2, what this really means is, and you know what, I'm going to introduce it here. X can be any numerical variable that we're talking about, right? So just a generic placeholder. X follows, so this little tilde here, you read as follows, normal distribution, centered on 30 with a spread of 2, right? And this spread is the standard deviation. So what this means is that down here, if we look at this normal distribution here, on my x-axis, or x-axis, I guess it's singular, I have my generic x's, okay? X can be GPAs or heights or speeds, any numerical variable, right, that follows a normal distribution. So x, right, all my measurements for x are down here on the x-axis. Not terribly confusing, but can be. The center, we know, is at mu equals 30. And then we're told that sigma is 2. Is it this part? Is it this part that's follows so it's a little tilde, think, like this. It's a little snazzy thing. And you read it as follows because we can have other distributions other than the normal, but so far we've only seen a normal. So how you read this, then, you read it as x follows a normal distribution with mean 30 and standard deviation 2. This is D. There's not really a spot to put your standard deviation, but you will need it for your calculations later on. And so often what I do is I just kind of jot it down kind of below the mean somewhere, kind of around that area so that I have both my numbers that I'll need. And spoiler alert, you'll need them for your calculations later. Okay. Okay, so that's a little bit of shorthand that I expect you to be comfortable reading, right? Not necessarily writing, but definitely reading, right? If I give you something like x follows a normal distribution 32, then you need to know what that means. Okay. Good. Any questions so far? I'm going to skip this example because it's kind of a lot of explaining for not that interesting of a problem. Anyways, if you can believe it, people exaggerate their heights on dating apps. Anyways, there's proof. You can read it on your own. I guess I can go, I guess there is something interesting, but I think it was both the males and the females. Whereas I think the initial hypothesis was that only males would exaggerate their heights in the upward direction, but they found the same thing for women. Maybe we just don't know how to measure ourselves. Ever think of that? So what do some normal distributions with different parameters look like? So remember, mu and sigma are from the population, right? Because they're Greek letters. And so that tells me that they're from the population, right? And so broad terminology, we call those parameters, right? And so parameters are measurements from the population, such as mu and sigma. So what do we have here? We have a normal distribution in both cases, of course, right? And so they look the same, kind of face value, they look the same, they have the same shape, fair enough. Triangle is a triangle is a triangle. Right? Where they differ are the parameters, right? And so I've got a mean of 0, which if you kind of trace it down, looks like it's centered on 0. And I have a mean of 19, right? So already I know that the second one is kind of shifted over to 19 off of 0, right? So they look the same, but they have different centers. The standard deviation of the first one is 1, okay? Whereas the standard deviation of the second one is 4. Now visually, I don't see a difference between these two. Okay? Where we will see a difference is if we put them on the same scale. Okay? And so here's our first distribution. This little guy is our normal 0, 1 distribution. And this little guy is our normal 19, 4 distribution. Right? We see the 19 is shifted over. Okay, fair enough. But then what happens when we increase the standard deviation? Kind of like squishes down, right? Why would it have to squish down? Because the total area is still 1, right? So you're always dealing with the same amount of area under the curve, right? It's just that now it has to accommodate more of a spread, right? And so then as the spread increases, right, things kind of smush down and start looking pancakey like this, right? Just allowing for more spread. Right? If we go back to where we have these kind of tick marks, right, then we see that, okay, I can move out 3 standard deviations, right, until I kind of stop caring about what's under the curve. We know that those tails, we call them the tails, right? Those tails don't close ever, right? But they start to get really, really tight pretty quickly. In fact, after 3 standard deviations, there's basically no area left. It's very, very small. Don't worry, we'll know how much area is left, but it's very, very small, okay? 0.15%. It's very small. Roughly. So here, notice that this is a distance of 3 sigma. And you can move out the other direction, right? If sigma is 1, then this is also a distance of 3 sigma. Now, between 31 and 19, well, I know it's 3 sigma. But now sigma is 4, right? Let's just confirm. So 19 plus 12, oh, math. Feeling good at 31 though. All right. So here, 3 times 4 makes a distance of 12, up from 19 puts me at 31, right? And so this 3 sigma is a distance of 12, whereas this 3 sigma was just 3, right? And so it had to cover a larger distance. And same thing, it had to move it in the other direction as well. I'll do 3 sigma equals 12. So that's going to be a rule that we'll establish eventually, where we can move out 3 standard deviations until there's really not a ton of area below the curve. So that's cool. Nice, good to know, I guess. Question?
Is it always gonna be 3, like no matter what?
Yeah, it's a property of the normal distribution. So. Now, area exists past these points, but not a lot. Right? The probability becomes so small. Right? Okay. So why do we need the table? Right? That big table that I handed out. Does anyone not have this table? One. And I knew it, I just wanted to play it cool, you know? My axe too, I bring it up a bit. We won't use it quite yet, but we will. So, let me see here, I'll bring up the table. Okay, maybe I can't resist. Yeah, where is it? Oh, I'm in the wrong. I lug these, nope, tables around. Even virtually. Oops. I want to show you, so this is the table that you have. Okay. It's called a Z table, or table A if you want, but a Z table. And so notice that it has a little Z up here in the corner. Okay. Now, what we're going to find, and I'm kind of working backwards here, trying something, is if you look at, here's a normal distribution. Right, this is supposed to be a hint at how to use the table. What it has on the x-axis is a z-score, okay, which means we need to know how to find these z-scores. Okay? These z-scores are standardized scores. Okay? And so we need to be able to find a z, right? And then we'll be able to give the table a z, and it'll tell us what? The table entry are all these guys. In fact, the table entry gives us the area to the left of that z-score. We haven't worked to that part yet, but I think it's nice to have kind of a sneak preview, and then we'll fill in the gaps as we go. Right? And so what are z-scores, or any standardized scores really? In the States, I don't even know if this is true still, but presumably you can write SAT exams or ACT exams. They're both college entry exams, right? But they're scored on different scales. Okay? So SAT scores are distributed nearly normally with a mean of 1,500 and a standard deviation of 300. How can we summarize that? using the notation that we have already. Oops, I went too far. SAT scores follow a normal distribution. Even if it says nearly normal, right, you're allowed to say that it follows a normal distribution with a mean of 1,500 and a standard deviation of 300. So you can really tighten up that first sentence using our shorthand. Right? Whereas ACT scores, I'll use green, are distributed nearly normally with a mean of 21 and a standard deviation of 5. So they're just on a smaller scale, right? But I think they're supposed to test similar things. So the ACT scores follow a normal distribution with a mean of 21 and a standard deviation of 5. You can imagine that a college admissions officer wants to determine which of the two applicants scored better on their standardized test with respect to the other test takers. Okay. Pam, who wrote the SATs and got 1,800, right? Or Jim, who scored 24 on his ACT exam. What are two things we know right away? Compared to the mean, right? Pam scored above the mean. That's good. Right, above average. And Jim scored above the mean. Right? But we don't know how much above the mean, right? Because we've got different spreads, right? I've got a spread of 300 and a spread of 5. I can't compare those directly, right? And so the move that we make is we say, well, what if we just said compared to the ACT distribution or the SAT distribution, right? Depending on which test they wrote, right? Compared to that distribution, how many standard deviations above the mean did each person score, right? Then we can standardize it. Huh? Was that in here? Or I don't know where that was from. It's in the computer. I don't know. And so here, we've got both our SAT scores and our ACT scores. So here we have our SAT scores, and here we have our ACT scores. You can score below the mean, you can score above the mean, right, with some variation. Now, presumably, there is a cap on the maximum number of points that you can get. We're ignoring that. We just assume that it can go into a negative score and a really, really high score. So we're ignoring that. Okay, so don't get hung up on that. Don't, but it doesn't really matter. But what we're going to do is to compare the scores we calculate how many standard deviations from the mean each score is. So we calculate how many standard deviations each score is from the mean. As you can imagine, it can be above the mean or it can be below the mean. So we need some standardized way of finding these values. So this is what we mean by finding standardized scores. confusing because these are standardized tests, but that's different. Standardized scores means that you can compare them apples to apples, right? They're on the same scale. I wrote it here because I find that if I write it, then you take it more seriously. But then it's on the next slide anyways. So standardizing with Z scores. Okay, this finally we see this Z that we got a table for. So obviously it's going to be a big player here for the normal distribution. And so that's what we're building up towards. But since we cannot just compare these two raw scores, we understand that. I don't think anyone would try to do that. We instead compare how many standard deviations beyond the mean each observation is. We say beyond because you can move in either direction of the mean. Right? PAM's score of 1800, right, is how far from the mean. If you subtract the mean, right, then and the reason we do the score minus the mean is because then I get a positive value if it's above, right? And I would get a negative value if it's below. Right? So that kind of tells me where this score is. And so here, this is her score minus the mean, and then divided by the standard deviation, right? And I think if I asked you to problem solve this, even if you didn't have this math here earlier, if I said, okay, I want you to calculate how many standard deviations Pam's score is above the mean, you would kind of get there, right? 1800 is how far from 1500, and then I divide 300 into that. Works out to be a nice even one, right? That's not always the case, but in this case it is. And so we find that Pam scored 1 standard deviation above the mean. Now Jim scored 24 on a test with a mean of 21 and a standard deviation of 5. So 24 is 3 from 21, or 3 above 21, and then divided by 5, I get 0.6. So 0.6 standard deviations above the mean. Gut reaction, that's not as good, right, as 1 standard deviation above the mean. Right, so now all of a sudden we can compare these scores. In fact, we can put them on the same scale, right? And so here we've got these standardized scores. Centered on 0. Jim would be at 0.6. I used green earlier. And Pam would be at 1. So you can tell that Pam scored slightly better than Jim on her standardized test, right? By comparing their standardized scores. 2 different standardizations though. Okay. So, did anything else? No, it's okay. I think I'll leave it. So standardizing with Z scores. So these standardized scores that we found are called Z scores, right? So Z scores, and I don't actually know where the Z came from. Interesting. I think at that point I was just ready to accept it as fact, because there's a Z distribution, a T distribution, an F distribution, a chi-squared distribution. And so there's all these other distributions that we'll see eventually. But so I don't know why it's Z actually, but I'll look into it maybe one day. So Z is a standardized score. And so any observation is going to be the value that you're interested in. So Jim's score, Pam's score, doesn't matter. That's your observation that you are interested in standardizing. And so in general, we have Z, which is the observation minus the mean, and then divided by the standard deviation. On your formula sheet, where is it? We're moving down. So here, the discrete random variables, this is the section that you would need for the bonus assignment if you wanted to do that. Otherwise, you can skip down to down here. I'll bring it into our notes here. Where? I think it's time for me to add a page. Oh, but I need lines desperately. There we go. Okay. So on your formula sheet, it looks like this. We're told that if X, right, SAT scores or ACT scores or GPAs or heights or weights or whatever follows a normal distribution with some mean mu and standard deviation sigma, right, then we use Z. Now, how do we read this? Z follows a normal distribution, right, centered on 0 with a standard deviation of 1. Right? And so that's what makes it standardized, is it's still the same shape, but it's always centered on 0, right? And the standard deviation is always 1. That's nice. I'll draw that out in a sec here, but just want to walk through here. So where the Z, how we calculate the Z, is going to be your X, the observation that you're interested in, minus the mean divided by your sigma. And there will come a time when you want to solve for the X, right? But we'll parking lot that for till probably next week. So here, what this means is that the Z distribution always looks like this. A normal distribution centered on 0 with a standard deviation of 1. And somewhere on here, you can say that what's on this line here, those are your Z scores. And maybe I should put it, I'm gonna scooch this over here and write it underneath. And this, you can rewrite as the observation minus the mean divided by sigma. Right, the thing that you're interested in is your observation, so that'll always be your X. We already established that I can fit 3 standard deviations on either side before I kind of run out of space. And so let's plop those down. Here I have 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean. keeping in mind that this thing keeps going still to positive infinity, right? Never closes. Huh? But after 3, we kind of run out of patience and it's too small. Huh? Same thing on the other side. Now, if I move down 1 standard deviation, I denote that with a -1, right? And so now my Z of -1, -2, -3. And again, it keeps going to negative infinity. So Z does keep going. And there's one assignment in particular where you will find a Z of like 13 or something crazy. And you'll text me late at night saying, I think I did it all wrong because I got a Z of 13 and that just can't be. But it can, because 13 is just a smidge from infinity, right? Kind of far off of infinity, actually, right? But it's just not a number that we're used to seeing, but it does exist. Yeah? It's just really, really far out into the tails. So just as a heads up. Okay, so what else do we know about the Z distribution? Well, it's a normal distribution. And so the total area under the curve must be 1, right? That's still true. Right? And so here, the total area is 1. That's always true for a normal distribution. Okay. We'll find that positive Z scores are above the mean, right? And negative Z scores are below the mean, right? So positive Z scores are above the mean, while negative Z scores are below the mean.
So it's a positive and negative infinity, but also still equal 1.
I know, right? It's this mind-boggling thing. And so you do need calculus to prove it, but so we just accept it as fact. But it is really mind-boggling. Right? Never closes, never closes, never closes, but it's still 1. It just is. But we leverage that fact a lot. So it's worth kind of logging, but it's true, and we just accept it as true for us. You can Google the proof if you want, but nah. What else about these Z scores? So we've got positive Z scores, which tell me something, right? It tells me that I'm above the mean. In fact, a positive Z score of 2 tells me that I'm 2 standard deviations above the mean. Okay. So a Z score, a Z score is the number of standard deviations an observation, and we just use the shorthand of X, so I'll put the observation X in brackets. And I guess I should put sigma over the standard deviations. So a Z score is the number of standard deviations an observation X is above or below the mean, which is our mu. So we know that SAT scores follow a normal distribution centered on 1500 with a standard deviation of 300. Right. What if we said find the z-score of the mean? So now the mean is 1500. So what that means is I'm gonna let x be 1500. How far is 1500 from 1500? 0 standard deviations, right? And so that's why z is always centered on 0. Yeah? And because of our calculations, right, it will always have a standard deviation of 1. So here then z, which is x minus mu over sigma, that's on your formula sheet, right? And we're going to use that a ton, right? Z must be 1500 minus 1500 divided by sigma, which is 300. So Z equals 0. And this is why Z is always centered on 0. Oh, where'd it go? This is why Z is centered on 0. Right? The mean is always going to be 0 standard deviations away from the mean. And then we can move out from there. Okay. Good. Going back to the previous slide, which I kind of left in the dust, z-scores are defined for distributions of any shape. So you're allowed to calculate standardized scores, z-scores, for any shape distribution. Okay? But only if it's normal can we use the z-scores to calculate percentiles. Now remember, the 3 P's all mean the same thing still. Right, percentages are probabilities, which are proportions, right? But in z-score terminology, we tend to use probabilities, right, to calculate percentiles or probabilities. Now we've talked about outliers before, right? And kind of being able to pick out outliers or extreme observations is part of the job, right? And determining, okay, this is an unusual observation that I'm seeing, right? I'm going to dig deeper into this. And so what we're going to find is that any observations that are more than 2 standard deviations away from the mean, are usually considered unusual. Well, this notation here, are you familiar with the absolute value? The absolute value of Z, if you put a negative into the absolute value, it just kind of drops the negative, right? And so really what this means visually is that Z is centered on 0. And if you're past the -2 or +2, we would consider those z-scores unusual, right? Kind of extreme. So here, unusual and unusual. Remembering that what I have on this lower axis here are z-scores. So just as a rule of thumb, any z-score bigger than 2 is going to be considered unusual. Now, what does unusual translate to in probabilities? Small probabilities, right? And so, and we'll see that. But unusual for us means the small probability of happening. That's what unusual means to us. Yeah. And in general too. Right? Probability is quite small, right? I don't expect it to happen all the time. It can, right? But what does that mean if I find a Z bigger than 3? Right? If I move even further out into the tails, then I would consider that even more unusual, right? So anything past 2, definitely past 3, we start to say, that seems strange. Right? And then it depends on what we want to do with that. But for now, we're just developing that gut reaction of, bigger than 2, huh? In either direction, of course, negative or positive. Right? We consider it unusual. Okay. Questions? Oh. We've seen percentiles before, right? With our Q1, our Q3s, our median. Remember that? It was so fun, boop, boop, boop. Probably not fun at the time, but now you're gonna think back and say, wow, that was so fun, right? So easy back then. No tables. I know. But we've seen percentiles before, right? A percentile is the percentage of observations that fall below a given data point. Yeah. Now, if we have a normal distribution, the percentile is the area below the probability distribution curve, which we just call the curve, to the left of that observation. Okay. And so what we're going to have is, this looks like Pam's score, 1800. Right. So here we've got our observation of interest. Right. Now we want to know, well, how many scored, or what percentage scored below Pam? Right. So here, Pth percentile. Instead of percentiles, we'll start calling them probabilities, right? But they are percentiles as well. Right? So just remember that the percentile is always below the observation, right? If you scored in the 90th percentile, what does that mean? It means that 90% of people scored below you and 10% scored above you, right? You don't want to sound silly and say, oh, I scored in the 10th percentile. What does that mean? You only scored better than 10% of the test takers. That's probably not good, not brag worthy, right? So you want to be careful, right? It's always the percentage below. Okay. So let's see here. Do I do it? No. Got a decision to make. No, I'll stick with the plan. So here, this is using R. I'm going to replace it with the Excel code that we would use, right? And of course, another Excel assignment coming at you, right? To learn how to use Excel instead of the tables that you've got, right? Like I said, these tables are quite archaic. You wouldn't use them in real life, right? There's online calculators, most calculators. And if you figure out how to use your calculator to find probabilities for Z scores, you're allowed to use that, right? Just kind of let me know so I don't think things are just appearing out of nowhere, right? But you're allowed to do that. I encourage you to do that. But I'll be using the table because that's what you'll have on the test. So those tables are yours to keep because you'll work with them quite a bit. But then, of course, on the test, you'll have a fresh formula sheet and a fresh set of tables to use. And then I reuse those. Don't worry, I reuse them. Now, I don't know if I've talked about R, but R is a statistical programming language. It's what's most commonly used if you're doing any sort of actual statistics. Now, for us, of course, we're using Excel. And so I'm going to cross this all out with Excel. But what you'll find is that it looks similar. Okay? And it produces similar results. If I can remember off the top of my head, you want to use equals norm dot s dot dist. Now it's really important that you use the dot s dot dist. Okay, there is a norm dot dist, and we use the norm dot s dot dist standardized. I might have to dig up my Excel. Where is my Excel? Here. Let's start a fresh one, I guess. All of mine are just brief. Sign in. I should be signed in already. This is crazy. I don't know. It's been too long. Okay. Does anyone else have access to theirs? If you go norm.s.dist, what pops up for the prompt? Is it Z? And then cumulative? I should have remembered. So if you type in norm.s.dist, I just want to know what it tells me to enter as the parameters.
17.
So it should look like cumulative. Like that? Okay. Good, thank you. Feel like I could have got there maybe, but I didn't want to risk it. So the norm.s.dist, what do? We give it a Z, right? And there are versions of it where you give it the X and the mean and the sigma, right? And it calculates that Z in the background for you, right? But I think it's nice in the beginning that we see the Z. Yeah? And so here you enter your Z, and for us, this cumulative is always going to be true. For the normal distribution, it will always be true. What does cumulative mean? Everyone always asks me at the beginning of the term, is the exam cumulative? Right? It means everything up to and including the final exam, right? And it means the same thing for the normal distribution, right? It means the entire area up to and including that point, right? And so for the normal distribution, we will always use true. Right? And it's explained in the Excel assignment as well. But I think in this case, because we should be using Excel for these probabilities, I wanted to introduce it. And so for normal distributions, we always use cumulative equals true. This says cumulative. I'll try again. Technically, the area at one point, right? If you think about an area of a rectangle, right? At a single point, if there's no base, right? Base times height makes the area of a rectangle, right? And if the base is 0, right, just at the one point, what's the area? Must be 0, right? And that's true for the normal distribution as well. But again, mind-boggling, because when you line them all up next to each other, all these areas of 0, you get areas. It's weird. But you also get a base, right? So we should use software, right? We use Excel, or if you want to poke around with, here's an online calculator that you can find, right? Just Google an online Z-score calculator, and they're usually quite helpful, right? They help you visualize things and you can play around with it. And so here, we will use tables to find probabilities in class. In class / on tests. But in real life, you would use software. Just so you're aware. And I really, really hate these tables. That's why I'm making a big fuss about it. Hate printing them. I hate using them. So for us, in class / on tests, we will use a Z table to find probabilities. Probabilities, which are areas under the curve. So here's a version of a Z table. We have one, right? It looks very similar. Right? You have one in front of you even. Looks like this. What you'll notice is, well, there's not really a first page, second page, but if we start over here on our negative Z's, right? So Z up in the corner, and I think it's kind of intuitive how you use this thing, right? So you've got your Z of negative 3.4, and then you've got your second decimal that you join up here. So if you have a Z of negative 3.47, negative 3.47, how we read this is that the area to the left of a Z of negative 3.47 is going to be very, very small, 0.0003. Right? Very, very small. So all this table has done is starting out here at negative 3.49. That's the smallest possible value that we have on the table. Of course, it goes to negative infinity, right? But starts there, and it says, hey, you're going to start with an area in the tail of 0.0002, right? Very, very small. After that, you can just say it's very small, like less than 0.0002. Right? And then we go by little check-in points, right? Negative 3.48, then negative 3.47, negative 3.46, 5, 4, 3, up. And then we can move through. It's just how you read it. You read it from right to left and then jump down the rows. So it can look like it's all hodgepodge, but it's not, right? Just because of how decimals work. So as we move our Z down, what does this mean? If I move down the line towards 0, I'm moving closer and closer to the mean, right? if I have a normal distribution, it's unimodal, it's symmetric. What do you expect the area to the left of the mean to be? If the total area is 1, I would expect it to be 0.5. Right? And so here at a z of negative 0.00 and 0, second decimal 0 as well, I have an area to the left of 0.5. Right? Then we can move to the positive value, or the positive side, the sunny side of the street here of the Z table. Right? So you just always want to make sure that you're working on the correct side. Right? And as we work more with this table, you'll find that you'll become comfortable with some shortcuts, right? So I'll introduce some shortcuts as we go, right? In fact, you only need one side of this table. And because by symmetry, it has to behave the same way on the other side, right? But that's for, next week maybe. And so again, if we pick up at Z is 0.00, right? That's in the center. I still have an area of 0.5, right? Another gut reaction, right? If I'm above the mean, I would expect all my areas below those Z scores, these positive Z scores, to be above 0.5. And so it's another good check-in point, right? Whereas if I have negative Z scores, I expect the area to the left to be less than 0.5. Notice that it doesn't matter which side you're on, right? Which side of the mean you're on, the Z table will always just give you the area to the left. Okay? And so if you really, really spend time with it, it doesn't look or feel like it now. I know that, okay? But this explains everything, okay? Which is why I use this particular table, because I like that it has the little shorthand explanation up at the top. Okay? Let's read it. We're told that this area is called a table entry. Right? We also need to know that these guys down here are the table entries. Okay. We're told that the Z is the Z score that I'm interested in finding a probability with, right? And so what it says here is the table entry for Z is the area under the standard normal curve to the left of Z, right? It's always going to give us to the left. That's okay. What if you need the area to the right? You can use the fact that you've got a total area of 1, right? And subtract it from 1. Subtract the area from the left from 1, and then you're off to the races. And go back here. So here's a version of the Z table, but you read them all the same way. So here we've got the whole number of Z, or the whole value of Z, and the first decimal place. And then up top, we have the second decimal place. If we're using the table, then that means we have to round our Z to 2 decimal places, right? In order to match the table, right? Whereas, of course, if you're using software, you don't have to do that. You lose accuracy by rounding, right? And so rounding's kind of, you don't want to do that. But if you're using the table, you do have to round properly, right? So if using the Z table, which we're not always doing, that's why I specify, yeah. But if we're using the Z table, we must round our Z score to 2 decimal places. Which I like to abbreviate DP. We say it a lot, and so decimal places, I usually just write DP. And that's to match the table. So it's not really something that you have to memorize. It's just you go to your table and you think, oh shoot, I need 2 decimal places. Then you go back and you round it. All right. So we go back to Pam's Z score. She scored 1 standard deviation above the rest of the SAT scores, right? The mean of the SAT scores. So that gave us a Z of 1. Right? So what that means is a Z of 1.00. Kind of boring, right? It'd be more interesting if we had more decimal places, which will happen, but we're just starting. Right? And so in this case, yeah, we are in the first column here. And what does this mean? It means she was at the 84.13 percentile. Percentile? Let's see here. I'll just add a page, I guess. Using the Z table, we find the area to the left of Z equal to 1.00, right? And I'll just tie it back to Pam's standardized score. Because it's been a while. So using the Z table, we find the area to the left of Z equals 1.00 is 0.8413. That's the area to the left. It's also the percentile, right? So therefore, Pam scored higher than 84.13% of other test takers. How many scored above her? Or I should say, not how many, I should say what percentage. It's kind of implied, but what percentage scored above Pam? Okay. And I'll bump this down. If we take it back to the original scale of the SAT scores, right, which is usually where we start our problem, right? We said that the mean is at 1500 and Pam scored 1800 and the standard deviation was 300. What we did is we found that Z, which is X minus mu over sigma, right? Where X is the value we're interested in, right? And so in terms of this question, what percentage scored above Pam? Right? To visualize that, that would be this area. You'll see that I don't tend to shade in the areas because it gets really overlappy and boggy really quickly. And so instead of doing that, usually how I show that I'm looking for this area is I draw an arrow in that direction instead. You're welcome to shade the area if that makes more sense to you, but we'll end up with lots of overlapping shaded areas and it just gets a little tricky. Whereas if you have something like this, right? If you're trying to shade these like this, it's hard to tell the difference with the shading, but the arrows are a little bit cleaner. You're allowed to, but I like and use the arrows on top to denote that those are the areas I want to find. Yeah. And so we want to find this area. Pretending we haven't done the work yet, but we already have. First thing we need to do is we need to standardize this score, right? The Z score, because in order to find the areas, right, I need to use the table. That's what the tables are for, right, is to find those areas. So I need a Z to be able to use the table, right? And so Z is 1800 minus 1500 divided by 300, which is a very boring Z equals 1.00 to 2 decimal places. Of course, that's not paste. Then, because I don't want to write this all out again, I'm just going to copy it and paste it here. Paste it there. Clean this up a little bit. So we already found this, right, using the table. How can I draw this? Here's a little weird move that we're allowed to make. It doesn't matter the scale, the probabilities will stay the same. So whether you're on a 1500, 300 scale or a 0, 1 scale, which Z is, right? It'll just map back to the same probabilities, right? And so what this means is this area is 0.8413. So I tend to only draw the original distribution, know that I need to find the Z, but then also that these probabilities stay the same no matter if I blow it back up to the original distribution or if I'm on the Z distribution, right? Kind of stays the same. So then, what does this area become? Knowing that the total area is 1, right? And so 1 minus 0.8413 is what? 1 minus 0.8413 is 0.1587. Or as a percentage, right? What percentage scored above Pam? 15.87% of test takers scored above Pam. But how I want you to write it, so you can show me with this drawing. Okay. Now, usually what happens is no one wants to draw the normal distribution and sketch it out, but I'll continue to do it. I encourage you to sketch out the distribution, okay? Especially on the test, when I give you a question like this, if you have drawn how you've understood the question, right? I can give you more part marks, even if you've misunderstood what to do in the question. If you've shown me in a drawing like this, hey, I'm looking for this area, whether that's true or not, I can give you more marks that way, right? If you show me how you understood this question to be asking you what to do, okay? And so always try to draw the distribution. It takes practice, right? But it will help you visualize what you want to solve. Okay? And so how you're going to write this is a continuation. So using the Z table, we find the area to the left of Z equals 1 is 0.8413. Therefore, the area to the right is 1 minus 0.8413, which is 0.1587. Which means 15.87% of test takers scored higher than Pam. Oops. Which is also a probability. The probability of scoring higher than Pam is 0.1587. That's more of a stretch, I know, but that's true as well. Yeah. So I mentioned Six Sigma, it's pretty big in business. And so anyways, the term Six Sigma process comes from this idea that if we're beyond, if you have 6 standard deviations between the process mean and the nearest specification limit, just kind of sets limits. Practically no items will fail to meet specifications, blah, blah, blah. Finally, a real example. We're ready for it. Now, can I just check something real quick? Because I can't remember if it's good or bad. Okay, I'm happy. Good. I just didn't want to have a boring number like 1 anymore. Pretty sure it didn't, but had to check. Okay. We're at a factory, at Heinz Ketchup Factory. The amounts which go into bottles of ketchup are supposed to be normally distributed with a mean of 36 ounces and a standard deviation of 0.11 ounces. Now we understand you go and you buy a bottle of ketchup, right? It says how much is in there, of course, but we also understand just kind of that that's not exactly how much is in there, right? There's variation and there's kind of reasonable variability. And then at some point, right, you would say, hey, anything below, and they have determined anything below 35.8 ounces, we can't ship that out. We have to recalibrate or whatever it is they do, right? Because these are underfilling and people will be unhappy, right? And so, right, you go and you grab a box of cereal. Hey, this doesn't feel like there's enough in here. You can complain about that, right? Same thing, ketchup. On the opposite end of the problem spectrum, right? Anything above 36.2 ounces, which is what they've determined, is you're overfilling these bottles, right? And so you're putting out more product, but you're not charging more. So then as a company, you're losing money, right? And so we've got these kind of limits, right? Underfilled, overfilled, anything within those limits, I'm happy and production can just keep moving. But as soon as I move beyond those 2 points, right, in either direction, then we have to stop and we have to recalibrate and kind of fire someone. No, I don't know, but right, something like that. Huh? And so what can we do with this information? Well, let's go back to the very beginning. The amounts are normally distributed with a mean of 36 and a standard deviation of 0.11. Okay? What I want you to do with that information immediately is to draw the curve, right? Jot that information down, right? You can write it in shorthand if you want to. Normal 36 and 0.11. But I want you to draw the curve as well. So before we do anything, I'm gonna draw it out. And I always forget, and it's also kind of hard to get to, but there's a normal distribution sticker, which I think is kind of cute. But I always forget. Anyways, I'll find it for next time. Might be in the science one or something. Anyways, should be in my recents, but it's not. So we've got the shape. Oops. The shape, normal. I've got a center. Oops. That's crooked. 36. And a standard deviation of 0.11. Yeah. And if you prefer, you can write mu as 36. Usually I get a little bit lazy and I don't write mu as 36, but it's a nice reminder. Especially since it's our first one. First real example here. Once every 30 minutes, a bottle is selected from the production line and its contents are noted precisely. If the amount in the ketchup bottle is below 35.8 or above 36.2, right, then the bottle fails the quality control inspection. Now here, what percent of bottles have less than 35.8 ounces of ketchup? So we're really only concerned with one of these extremes, but we can jot them both down, right? Underfilled is anything less than 35.8 ounces, which we know is below the mean. Now, when you're drawing these, it's just to visualize where things are. So the only really important part is that you're on the correct side of the mean, right? And so what I'm going to do, instead of spending time and thinking about, oh, a standard deviation of 0.11, all I'm really looking for is 35.8 is somewhere below the mean, right? And I like to give myself enough space, right? So it's just to visualize this thing. So here, these guys are all underfilled. All right. And remember, on this lower scale, this kind of axis that we're working on, right? Those are is it the weights or the amounts, the ketchup amounts, right, in ounces. Okay, so of course it's decreasing as you move out. These are underfilled. And on the flip side, 36.2 is above 36. So really in terms of my visualization here, just gonna plop it down 36.2. We can also find the probability of them being overfilled. Right. This question in particular is not asking for that. And I should, but if it doesn't later, we'll do that one as well. Okay. Can I change the 36.2 to something more interesting? Why do I think it's boring? Let's talk about that. 35.8 is 0.2 below 36, right? And 36.2 is 0.2 above 36. What does that tell me? Well, they're on the same standard deviation scale, and so I would just get a positive version and a negative version of the same z-score. Fine. It's boring, but it's okay. Should change it. 36.5. Ah, crazy. No, we'll stick with it as it is. In fact, we're really only asking what percent of bottles have less than 35.8 ounces of ketchup. No? So in terms of what we want to find, right? We want to find, you can shade this area if you like that, or I like to put a little question mark just with an arrow coming up from 35.8, right? This 35.8 is my observation of interest. The thing I want to find a percentage or a probability associated with, which makes it my X. If the end goal is to find a probability, right, which I can then multiply by 100 to get a percentage, right? What percentage, but first we need to find the probability. There's kind of a gateway that we need to use. So if you have an X, an observation, 35.8 ounces, what you need to do is you need to morph that into a Z, right? And so how do you do that? Well, you use Z as X minus mu over sigma. So you plug in your X, your mu, and your sigma, and you calculate Z. Once you have a Z, then you can get to a probability using the Z table. Right? You need a Z to use the Z table, but from the Z table, you can find the probability. Okay. Next week, no surprise, I'm giving it all away, I guess. We can always start with a probability, use the Z table backwards, basically, from how we learned it, graph it to a Z, and then use that as our Z in our formula to solve for the X that makes that happen. Right? What do the lowest 10% of ketchup bottles weigh? Right? That's what that would look like. I give you a probability, you map it back to a Z, and then you can solve for X. But that's for next week. But just as a heads up, we can still move through the other way. Right? So we'll be able to move backwards and forwards. But for now, we're just learning the forwards way. But just be aware. Okie dokie. Once you have your mean and your standard deviation and you've kind of sketched out the problem, right? Then the value that's below kind of where you want to find the area with, that is your X, right? I would say figuring out what your X is might be the hardest part. Okay. After that, Z is X minus mu over sigma. So in terms of, so first you have to figure out, okay, do I have an X or do I have a probability? Right? In our case, we have an X, 35.8 ounces. I need to turn it into a Z, so I need to use this formula. Here we go. 35.8. How far is it from 36? The mean of 36 with the standard deviation of 0.11. 35.8 minus 36, then divided by 0.11. I get Z is negative 1.81818, repeating. That's technically true, and software would be able to give you a probability associated with that repeating number, but the table cannot. We need to round to 2 decimal places properly, right? And so Z is roughly negative 1.82 to 2 decimal places, right? The number is followed by anything 5 or greater, you have to round up, otherwise you round down. Okay, so RZ is negative 1.82, which really means that any ketchup bottle that's 1.82 standard deviations below the mean is considered underfilled. So now we go to our table, which is why it was so important that I remembered to bring them to you. Bring them for you, I guess. Bring them to you. How are we going to do this? It's negative. So you want to make sure you're on the negative side of the Z table. Okay. We have a Z. I'll just jot it down here. Negative 1.82. From our question. Which means that our whole number is negative 1, and then our first decimal is 8, and our second decimal is 2. You want to be really careful, especially, so for some reason, those ones didn't print with these kind of shaded areas. And so what I would recommend doing is just kind of use a different piece of paper as a straight edge. Otherwise, your eyes will jump around and you'll just kind of grab the wrong number. So just be really careful when you read the table, right? I like to highlight like this, of course, but that's not always doable. So here, at the overlap, what does this mean? Means the area to the left is 0.0344. So now I'm going to remember that, 0.0344. And I'm going to replace it here, 0.0344. I like to jot it down there, but then I also like to write it out in words exactly what we did. I encourage you to do the same. Because you're just explaining what you did. It's not hard, it's just kind of tedious. So what does that look like? Using the Z table, right? Just explaining what you did. We find the area to the left of Z equal to negative 1.82 is 0.0344. Therefore, right, that is the area we're looking for. So we're done, right? 3.44% of bottles are underfilled, right? Or have less than 35.8 ounces. But let's just call it underfilled. Therefore, 3.44%, right? Just multiplying by 100 of bottles are underfilled. Ah, nice. If you find writing this annoying, you're allowed to use shorthand. What's the shorthand for this though? Back to probability notation, so it's a probability. What's it the probability of? The probability that Z is less than or equal to negative 1.82 is equal to 0.0344. That's giving the same information. It's giving the same information as this long blurb. Okay. So you've got kind of two options. If you feel comfortable writing it with the shorthand, you're allowed to do that. Just be careful that what you're saying makes sense. Okay. Or just write it out in words. Using the Z table, we find the area to the left of Z equals negative 1.82 is 0.0344. The probability that Z is less than or equal to negative 1.82 is 0.0344. Saying the same thing, one slightly shorter, but a lot harder to kind of master. Right? I'll keep writing both versions so you can see them, right? But if you want to just stick with this one, the words, totally fine. Huh? How am I doing? How about I'll leave this one so we can start here, but I want you to try it. What percent of bottles pass the quality control inspection? What area are you looking for? This area, right? Between 35.8 and 36.2. Ah, let you think on that over the weekend. There. Try this for Tuesday. If you have any questions, let me know. Otherwise, enjoy your weekend and I'll see you on Tuesday.